In this video, we're going to wrap up the last couple of things regarding the lim sup and lim inf. So we're going to start off with proposition 1.3.18. So let's say we've got a sequence of real numbers, and the result here is that there are two subsequences, maybe only one if it's a convergent sequence, but there are subsequences. A n sub k and a m sub k such that a n sub k converges to the lim sup of the original series, and the other sequence am sub k converges to the lim inf of the original series. And let's prove this. Actually, we're going to prove this only in a special case. So technically you need to prove this separately for the lim sup and the lim inf, and you also want to consider the cases where a is a real number and a is infinite separately, but I'm going to prove one of those four cases, and we're going to leave the other three cases as exercises. So let's say a little bit about what our assumption means. So we're going to let A be lim sup n is the limit as n goes to infinity, the supremum of all the AKs such that k is greater than or equal to n. So A is a limit. So as n goes to infinity, this supremum is heading towards A. So that means by our epsilon n characterization of limit, so if epsilon is a positive number, then there is a natural number n. Let's write this as n of epsilon to emphasize that what your n is depends on what your epsilon, such that if n is bigger than big N, then this supremum is within epsilon units of our number A. So that is what it means for A to be the supremum. And we're going to construct a subsequence of the A's. So we're going to construct a subsequence based on a sequence of epsilons. So what we need is a sequence of numbers of positive numbers that are tending towards zero. We're going to think of that as being a sequence of epsilons. So we're going to let n sub j be n of epsilon equals 1 over j. So we're going to take our epsilons to be 1, 1/2, 1/3, 1/4, and so on. You could take it as 1, 1/2, 1/4, 1/8. So if you wanted, this is just pretty straightforward to write down. So let's draw a picture of what's going on. Here is a nice line at level A, and then we draw another line, a distance 1 over j above it, and then our sequence, maybe we bounce around, but eventually we get to the point where we're stuck underneath this line, where our supremum, everything's under that line. So let's see, here would be our n sub j. Now it's sort of tempting to let our subsequence be a sub n sub j. We've defined an n sub j, but there's two problems with that. The first problem is that your n sub j's might pile up on top of each other. You might get to within, say, 1/8 of your target A all in one go, and then N1, N2, N3, N4 up to N8 might all be the same number, and you're not supposed to have that for subsequences. More importantly, the limit supremum sort of only cares about upper bounds. In this case, we see that our n sub j point, it might be quite far down below our target A, just as long as there's something close to A, not too much above it further on. So we're going to have to do a little bit more work. So here's how we're going to do this. So we're going to let n1 is bigger than n sub j, greater than or equal to n sub 1. And so it is one of the k's in that supremum akk greater than or equal to n. Sorry, this n here needs to be a capital N, and so the other thing we want our N1 to do is that supremum is that we want a sub n sub 1 to be. We can't insist that it actually equal the supremum of the AKs such that K is greater than n sub 1. But we can insist AN1 has to be arbitrarily close to it. Let's say we also have to be within 1 over 1 of the supremum, and if you think about it a little while, you'll see that you can require this. And then we're going to let N2 be at least the maximum of N2 and N sub 1, and we want this to be a subsequence, so increasing, so we'll make it N sub 1 plus 1. And AN2 is greater than supremum of the AKs, where K is greater than let's use the same number, or the maximum of n2 and n1 plus 1, and no, minus a half, and notice the limit supremum, it's a limit of a decreasing sequence because you're taking the supremum of smaller and smaller sets, so any of the supremums along the way, they can't be any smaller than your limit, than your a minus a half. So, in general, we're going to let n sub j, it has to be bigger than nj minus, than n sub j, big N sub j, and then also bigger than our previous element in our increasing sequence. And we also require that a n sub j is bigger than the supremum of ak's, where k is bigger than exactly the same thing, same sort of thing we saw before. Then let's write out what we know about our a n sub j's. So we've got a minus 1 over j is strictly less than a sub n sub j. But n sub j, little n sub j, remember, is at least big N sub j, so this is less than or equal to the supremum of the ak's, such that k is bigger than big N sub j, which by definition of big N sub j can't be any more than a plus 1 over j. So rearranging things, a minus a sub n sub j is less than 1 over j for all j, and thus a n sub j is converging to a, and you can check this using the epsilon n definition, this time taking n bigger than, say, 1 over epsilon. You just find a 1 over j that's less than your epsilon, and you take your n far enough out. We're going to finish up section 1.3 with the following corollary. This is corollary 1.3.19. So we're going to let n be a sequence of real numbers. And then two things we're going to prove. First thing is that if the limit supremum of the ANs is bigger than some number A, then there are infinitely many AKs such that with AK bigger than K, and conversely, if A is bigger than the lim sup, there are finitely many an bigger than a, so you can put this another way. There is a natural number n such that if k is bigger than n, then ak is less than a. And that means that only finitely many of them can actually be bigger than a. In fact, at most, big N of them. So here is the proof befitting a corollary. The proof is pretty quick. So for part A, we let a sub n sub k converge to a, which is equal to our soup of the ANs. And let's let epsilon be our a, the lim sup, minus a, the target number. We're using the letter A far too often in this problem. Sorry about that. And we're going to let k be such that if little k is bigger than big K, then ANK minus A is less than epsilon, and if you work through the absolute values, or ANK has to be bigger than A minus epsilon, which is our big A, and there are infinitely many such K, so that means there's infinitely many ANKs, which are all ultimately ANs that are bigger than big A. All right, and then the proof of part B is lim sup AN equals A is less than A. We let epsilon be the opposite, A minus A, because now big A is bigger than little a, and we need epsilon to be positive. And we let K be such that A minus sup AN and bigger than K is less than epsilon, which we can write slightly differently as sup and for n bigger than RK has to be less than little a plus epsilon equals big A. So I suppose, actually let us name this number capital N and not capital K, because this is the very N in our statement of part B. And then we just use little k instead of little n. And that completes the proof. In this video, we are going to begin section 1.4 in your book, which is the section on infinite series. So here's how we start this. We're going to let n be a series, a sequence, and then this thing is also a sequence. You take the sum from n equals 1 to m. That's a sum of finitely many numbers. That's a number for each m. This is also a sequence. But it's a sequence you build by summing another sequence. And we refer to this thing as a series, and or we can use an infinite sum from n equals 1 to infinity. An is going to denote our sequence of partial sums. And then definition 1.4.1 is that if the sequence of partial sums, if that's viewed as a sequence, converges to S for some real number S, we're going to say the series is convergent and two different ways to say this. Some n equals 1 to infinity, an converges to S, or when we want to be very concise, we just write the infinite series an equals S, and we just remember that this equal sign is representing convergence and not any simpler form of equality. And sometimes there isn't an S, sometimes this sequence of partial sums is just a non-convergent sequence, and the term for that is diverges. And the first proposition we're going to prove about these things, this is proposition 1.4.2, is that if the sum from n equals 1 to infinity, if your series converges, then the sequence converges. And not only does it have to converge, but I can tell you what it converges to. It converges to 0. The series can sum to something different from 0, but the sequence, the things you're adding up, the individual pieces, they have to converge to 0. And let's write out the proof of this. So let's let SM be our partial sum. So by assumption, SM converges to S for some S in R, some real number S. So, for all epsilon bigger than 0, there is a n bigger than 0 such that if our m is bigger than n, then SM minus S, let's make it less than epsilon over 2. We can force this as small as we want. I want to force this less than epsilon over 2. So I suppose sneakily there is we direct the reader to pick a positive epsilon somewhere in here, but let's move on. If n is bigger than n, then let's write absolute value of an minus 0. We're trying to show an converges to 0, so we want an minus 0 to be small. That's the absolute value of an. But then we can write this as S sub n. You add up the first n and then you throw the rest of them away, S sub n minus 1. Let's go ahead and make this let's make this an n plus 1 actually. And then what we can do is we can go ahead and use the triangle inequality. This is at most Sn minus S, and then we add to that Sn minus 1 minus S. We've got two things that are both getting close to S, but then because I made the little n bigger than big N plus 1, little n minus 1 is also bigger than big N, so these pieces are both less than epsilon over 2. And so we have seen that for any epsilon, there is a big N such that an minus 0 is less than epsilon, so an is indeed converging to 0. Now, this is a necessary condition for the series to converge, but it's not sufficient. If the only way the series can converge is if the ANs go to 0, but it is possible for the ANs to go to 0 and have the series diverge, and there's a very classical, very well-known example of this. It's called the harmonic series. We just let an be 1 over n. Then an is certainly converging to 0. But our series is going to diverge. And here's why that is true. So let's write out the first few terms. N equals 1. Sorry, this really must be a sum from n equals 1. I do not want to start with a0 because a0 is 1 over 0. So, and that's no good. So, sum from n equals 1 to m of an. That's 1, and then a half, and then a third, and then a fourth, up to 1 over m. And now this is at least, all right, the 1 and the 1/2 we're going to leave the same. And then the third and the fourth we're going to drop that down to a fourth plus a fourth. And then, let's see, we'd have a fifth and a sixth and a seventh and an eighth and a ninth. We're going to drop those ones all down to an eighth and an eighth and an eighth and an eighth. And then, so we've got a half, 2/4, 4/8. Not going to write them out, but we're going to have 8/16, and so on. And then we notice that if we group these two, we get a half. If we group these four, we get a half. If we group these 8, we get a half, and so on. So what we end up with is at least our 1 and then our floor of the logarithm base 2 of m. So if m is 2, we get 1/2. If m is 2 squared is 4, we get 2/2. If m is 8 is 2 cubed, we get 3/2. But the point is the logarithm base 2 of m goes to infinity. So the limit as m goes to infinity of the partial sums of the harmonic series, that is infinity. So we keep getting bigger and bigger. And with series, we really do want to say that to converge, you have to converge to a real number, not to infinity. In particular, the proposition 1.4.2 doesn't work if you think converging to infinity counts as converging 1 plus 1 plus 1 plus 1 plus 1, or 1 plus 2 plus 3 plus 4 plus 5. Those converge to infinity, but the individual terms aren't going to 0, and we really do want proposition 1.4.2, so we're going to think of convergence as meaning convergence to a real number, to a finite number. Now I am going to talk about a very famous convergence series, or at least a series that usually converges. So this is proposition 1.4.4. So let's let x be a real number. Then if x is between -1 and 1, so if the absolute value of x is less than 1, then the following series, we start at x to the 0, which is 1, and by convention we're going to say 0 to the 0 is 1. Then this series converges to, and I can even tell you what it converges to. It converges to 1 over 1 minus x. And if the modulus of x is 1, if it's 1 or minus 1 or bigger than 1 or less than minus 1, the series diverges. All right, and let us go ahead and prove this. Let's let S be the sum from n equals 0 to some finite number m of x to the n. So S is a partial sum. And let's write out what S is equal to. Let's do some scratch work. S we can write as 1, and then an x squared, and then we keep going, and then we get up to an x to the m. So now we've got m plus 1 terms in total. X to the 0, x to the 1, x squared up to x to the m. So I'm going to leave the 1 out front, and I'm going to factor an x out of what's left. That thing in parentheses looks an awful lot like S. We're just stopping one term too soon. So what I am going to do is I am going to add that extra term back in. xm, and then we just have to subtract it off, x minus x to the m plus 1. So we're left with S equaling 1 plus x times S minus x to the m plus 1. And then we're going to take this leftover piece, this excess, and we'll subtract that off to the other side. We'll get S minus x times S is 1 minus x to the m plus 1. And we can also write this out a little bit more formally using sigma notation. So let's go ahead and just use what we've already written as S minus the excess. That's sum from n equals 0 to m x to the n minus x sum from n equals 0 to m x to the n. Move the x inside, and then in our second sum we let k be n plus 1. This is like a change of variables in an integral, except it's in a summation. Then we can just reorganize this so that everything is using the same indices. So we've got our x to the 0, sum from n equals 1 to the m, x to the n, minus sum from k equals 1 to the m, x to the k, minus an x to the m plus 1, and then obviously our middle two sums cancel. And we're just left with 1 minus x to the m plus 1. So in either case, sum from n equals 0 to m x to the n is 1 minus x to the m plus 1 over 1 minus x, provided x is not equal to 1, so we're not dividing by 0. If the absolute value of x is less than 1, then x to the m plus 1 converges to 0. That is proposition 1.4.2. That is not a proposition, that is exercise 1.3.11b, which we assigned for homework. So our sequence of partial sums is converging to exactly the thing that our problem statement said it was converging to, 1 over 1 minus x. We're left with the x bigger than 1 case, but if the absolute value of x is greater than 1, then the absolute value of x to the m plus 1, absolute value of x to the m times x, absolute value of x to the m times absolute value of x. Since everything's positive, that's greater than, I suppose this should be the greater than or equals to case. Absolute value of x to the m So, by a straightforward induction argument, x to the n is at least 1 for all n at least 1. Thus, x to the n is not allowed to converge to 0. It can't be a sequence that converges to 0. So by very first proposition in section 1.4, our sequence of x to the n's diverges.